I will. I will begin with a word of prayer. Ahem. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you just bless our work today, Lord. In your name I pray. Amen. So I thought before I dive into partial fractions, let me just take a minute just to talk about problem 6, right? And the mission. And so, I mean, technically speaking, my wording is a little bit loose in that problem. For example, I didn't tell you, I say that the circle, the wheel travels along the line segment, right? What I mean by that is that the wheel is attached, like its center is attached at the line segment, as drawn in the picture. So here's like a picture of time 0. At time 0, the wheel, which I've made red, is attached to the 3, 5 point. And then I say, I want you to give me the equations of motion for a light on the rim of the wheel, all right? And I tell you that the light on the rim of the wheel starts at 5, 5, also at time 0, right? So I'll make that green here. So this point right here is what you're trying to find the equation of, parameterization for that point. And so what I describe in the problem is that this wheel is turning, right? And I didn't actually say if it was clockwise or counterclockwise, but just make it counterclockwise to make your life easy. See, I made your life easy because I put the point where, right? Just horizontal to the center of the circle. So that makes the equations for parameterizing the red circle pretty easy if you just ignore the center being 3, 5. So you could imagine that the red circle was at the origin. You could write down equations for that pretty easy. Now, at a future time, it's up here somewhere, right? And I'm not sure exactly where that... This is, by the way, rotating 10 times per second, right? So that's pretty fast relative to the motion of the... well, let's see here. How long does it take to get from 3, 5 to minus 213? Well, if you use 0 less than t less than 1, it takes 1 second. So that means that that light revolves around its center 20 times by the time you get up to the other point, right? Because I wanted you to get 20 revolutions per second for the light. So it's really, it'd be hard for me to really graph the curve that we're talking about. I mean, it's something like, that, 20, right? 20 times. So you're trying to parameterize something like that green curve. But it's relatively simple because you can break it up into 2 pieces. The one is to find this right here, which I'll call R2, right? And the other is to find R1, right? And so, and I'm saying you can continue doing that. Like up here, this would be R1 at time t, and of course I don't know exactly where the light is at that point because it's it's hard to say. It's complicated, but it's somewhere in there, right? And so this would be R2 of t, and so what would be at any point? At any point, to get from the origin all the way up to where you are, that's R of t equals to R1 of t plus R2 of t. So this is how you can parameterize that rather complicated motion. Break it into pieces. Figure out how to get a path which goes from the center of the circle out to the rim, which is rotating around 20 times per second. That's what I've called R2. And then find a parameterization that moves you along that line segment from time 0 to time 1. That's what I've called R1. Take the sum of those two. That describes the rather complicated motion of that point on the rim of the circle. And that gives you a parameterization that you're looking for in problem 6. You've already found R1 of t in problem 5. All right? So anyway, that's a little bit more guidance. I know that the actual words in that problem, you're like, what do you mean the circle goes along the line segment? This is what I mean, all right? Any questions about that? All right. So today we're talking about partial fractions, all right? We're talking about so-called partial fractions decomposition. Partial fractions, or how to use the partial fractal decomposition to integrate. So what on earth is the partial fractal decomposition? Okay, well, here's the big picture. Big idea. Any rational function f of x equal to p of x over q of x can be decomposed into a sum of basic rational functions and possibly a polynomial. So to give you the big picture, p of x here and q of x are polynomials, right? A rational function is the quotient of two polynomials. And, you know, if I just write down a rational function, you can't integrate it necessarily. But, in fact, if you look at the basic rational functions, we already have the tools to integrate every last one of those. So by finding the partial fractions decomposition of a rational function, it allows us to integrate any rational function. But of course, finding the partial fractions decomposition requires some effort. All right? So let's try to describe what I mean by that. I'm going to illustrate with a series of examples. Okay? Example 1. Suppose we have f of x equals to 1 over x squared plus 3x plus 2. And well, I'll make it a little bit more interesting. Let's suppose it's 2x minus 7, right? Okay, so what we do here is we go, well, that is 2x minus 7 over x plus 1 times x plus 2, right? The denominator here factors. And so what the technique of partial fractal decomposition says is, whoa, if your denominator factors like that, all right, then supposing that the numerator is not quadratic. Is the numerator quadratic? Well, no. Numerator here is linear, right? Then the partial fractions decomposition has the following form. We can write that as a over x plus 1 plus b over x plus 2. This is the claim. It's a theorem of algebra that there exists a and b to make this so. All right? Can we find the a and b? How do we find the a and b? Currently unknown. They will be known to us pretty soon, right? About 2 minutes. Let's do the algebra. So what I do is I multiply both sides by the denominator. Right? And to be clear, I'm going to take this equation here, star, and I'm multiplying star by that. What happens when we multiply star by the denominator? Right? On the left-hand side, right? So multiply by both sides by the denominator, distribute as we can, right? And you see what cancels. There's lots of reductions here, right? Like this cancels with that. This cancels with that. This cancels with that. What does that leave us with? 2x minus 7 equals to a times x plus 2 plus b times x plus 1. So we need to figure out what are the values of a and b. Any ideas on how we should do that? Yeah.
A or b equal to 0.
Set a or b equal to 0. Well, I'm trying to find a and b. How do I know they're 0? I mean, if a happens to be 7, setting it equal to 0 is not going to help us. But making things 0 is a good idea. What could we make? Yeah. So if we put x equal to minus 1, so what I do is I say x equals minus 1 like this. That tells the reader I'm putting x equal to minus 1. And then I do that. So that's what? Minus 2 minus 7 equals a times minus 1 plus 2 plus b times, well, 0, right? So that's a good choice because that gives us a is equal to, well, that says minus 9 is equal to a. Hey, well, there's one. What do you think? What do you think we should do next? Same thing with x equal to what? Negative 2. All right. So we got minus 4 minus 7 is a times 0 plus b times minus 2 plus 1, which tells me that minus 11 equals to minus b. Therefore, b is equal to 11. All right? And I'm going to put the conclusion over here in the corner if you guys don't mind. So therefore, the partial fractions decomposition, which I'm going to abbreviate PFD because writing partial fractions decomposition like 30 times in this lecture sounds annoying. So let's just invent an abbreviation, PFD. Yeah. So the partial fractions decomposition is, in particular, 2x minus 7 over x squared plus 3x plus 2 is equal to what? It's equal to, I'll write the b one first since it's positive. I got an 11 over x plus 2 minus 9 over x plus 1. All right? Can you integrate? Notice that integrating the left-hand side, I don't know. Integrating the right-hand side, piece of cake, right? You can see that the integral of f of x dx here is equal to 11 times the integral of dx over x plus 2 minus 9 times the integral of dx over x plus 1, which of course is 11 natural log of the absolute value of x plus 2 minus 9 natural log of the absolute value of x plus 1 plus a constant. And there you go. Integrated. So looks like there's a good chance that if our rational function is like a linear over a quadratic where the quadratic is distinct linear factors, we can do an integral just like this, right? What are other possibilities? If we're still looking at like a linear over a quadratic, what else could happen? What if we had linear over irreducible quadratic? How would we deal with that? For example, what if we had the integral of, say, 3x divided by x squared plus 4x plus 5. So in this case, there is no partial fractions to do. The partial fractions decomposition is already done. Like, this is already a basic rational function, actually. I can't further break it down because x squared plus 4x plus 5 does not factor over the reals. We can complete the square in the denominator, and we get, well, all right, fine. So that's x plus 2 squared plus 1. So, in other words, irreducible, right? Irreducible quadratic. If you looked at the graph y equals to that, there'd be no x-intercepts. So in this case, what you do is, well, there's a variety of different ways you could attack it, but the way I would attack such a thing is to create an x plus 2 upstairs. So that's x plus 2, and then that would have to subtract 6. Now, the reason I did that is so that I can break the integral up into two pieces, the one of which I'm going to be able to do a u substitution on, and the other of which I could use a trigonometric substitution, or, I mean, it depends on how you want to look at it, but here, let me just go ahead here. So we got 3 times x plus 2 dx over x plus 2 quantity squared plus 1 minus 6 times the integral of dx over x plus 2 quantity squared plus 1. So let me suggest that this one, we can make a w equals to x plus 2 squared plus 1 is a substitution, right? If I make that substitution, then what's dw? It's 2 times x plus 2 dx, right? For the other one, I can make a u equals x plus 2 substitution. Then, of course, du would be equal to dx. With those substitutions in mind, which I'll sort of partition off here if you don't mind, this reads what? Integral of, so we got 3/2 integral of dw over w minus 6 integral of du over u squared plus 1. These are integrals that we can do, right? So, 3/2 natural log the absolute value of w minus 6 inverse tangent of u plus a constant. Now we go back to the x's. 3/2 natural log the absolute value of x, x squared plus 4x plus 5 minus 6 times the inverse tangent of x plus 2 plus a constant. And there you go. So if we face a linear divided by an irreducible quadratic, we complete the square, and then we can split the integral into two pieces, the one of which is like an inverse tangent, the other piece which is just amenable to make a substitution of the denominator, just a basic, well, in this case, w substitution, all right? So this kind of basic rational function, a linear over a quadratic, we can deal with like this, all right? So what if we face something like f of x equal to, say, x squared plus 3x minus 7 over x squared plus 6x plus 5? How do we integrate something like this? So this is different than the first two examples. The first two examples, we've been looking at a rational function which is called a proper rational function. This is an example of an improper rational function. Because the degree of the numerator is greater than or equal to the degree of the denominator. Right? In this case, they're equal. If you encounter such a thing, you either have to do long division or some kind of simple trick to rewrite it as the sum of a polynomial plus a rational function. Now this one, I can use a kind of silly trick to, I don't really need to do the long division. I'll soon show you an example where long division isn't unavoidable, but this one, we can, let me show you a dirty trick that will serve us well. So just imagine that you have 6x plus, x squared plus 6x plus 5 upstairs. Now that's not true, right? But to be fair, how can you make it true? What do we have to add? What correction do I need to make this so? Minus 3x. And I have to have a minus 7, right? But I have a 5. What'd you say? Minus 12? Do you guys agree? If you take what's in the numerator on the right-hand side and you simplify it, you get the numerator on the left-hand side, right? So, and the reason to do this is pretty simple. If we have the pattern a plus b over c, well, that's equal to a over c plus b over c, right? But thinking of this whole first bit as quote-unquote a, right? That gives us x squared plus 6x plus 5 over x squared plus 6x plus 5 minus 3x plus 12 divided by x squared plus 6x plus 5. I just pulled the minus out. And of course, the first thing is what? It's just 1, right? So here we go. This is 1 minus 3x plus 12 divided by x squared plus 6x plus 5. So this is not yet the partial fractal decomposition, but it's getting closer to it. At least we found the so-called polynomial piece. 1 is a polynomial. It's a kind of stupid polynomial, but it is a constant polynomial. Now, to decompose the basic rational function, excuse me, not basic, but now this guy is a proper rational function. Proper rational function is the thing we do the partial fractal decomposition on. So how to do that? Factor the denominator. So x squared plus 6x plus 5, which is 3x plus 12, divided by what? X plus 1 times x plus 5. Right? And so partial fractions says, hey, you know what? I can find a big A over x plus 1 plus a big B over x plus 5, which will achieve this decomposition. How do I find the A and the B? I find A and B exactly as I did in example 1, focusing on the part that I'm manipulating, right? The 1 out front doesn't have anything to do with it, and I'm ignoring the minus for the moment. Right? I'm going to need to put that minus back in before I can actually finish the integration if I want to. Okay. So multiply star by, x plus 1 times x plus 5. This is star. And we get we get 3x plus 12 equals a times x plus 5 plus b times x plus 1. Part of the challenge of calculus is learning for yourself what you should write down. Right? In the first example, I wrote down the explicit multiplication by the denominator on both sides, right? And then I showed that these cancel. And I think it's good for you to see that once, but we don't need to write all of that detail out in every one of these every time. It's not an unreasonable assumption to assume that you can think about these cancellations in your mind and write down the answer. Something to think about. Everything that you write down is an opportunity to make a mistake. Every new line you write. I know there's a balance to be. Not writing things down also allows for making mistakes. I don't know. There's some kind of balance to be struck between writing too much and writing too little. If you write nothing, well, I'll take off points for not showing credit. There's always that. But I think this leap that I just made is a reasonable one to make. Is all I'm saying. All right. Now, what do? Well, how about we put x equals to minus 5, and we put x equals to minus 1 and see what happens. X equals to minus 5 gives me minus 15 plus 12 equals to a times 0 plus b times minus 4. X equal to minus 1 gives me minus 3 plus 12 equals to a times, 4 plus b times 0. So the first equation implies that minus 4b is equal to minus 3. The second equation implies that 9 is equal to 4a. Therefore, b is 3/4, and a is apparently 9/4. Let me then summarize our work. Therefore, summarizing our calculations, we have that x squared plus 3x minus 7 divided by x squared plus 6x plus 5 has the following decomposition. It's equal to 1 minus 9/4, 1 over x plus 1, minus 3/4, 1 over x plus 5. And that's the partial fractions decomposition for this rational function, right? Including the starting polynomial piece. What I just wrote in brown, I think everybody here can integrate, right? Can you integrate that? The integral of x squared plus 3x minus 7 over x squared plus 6x plus 5 dx is equal to x minus 9/4 natural log the absolute value of x plus 1 minus 3/4 natural log the absolute value of x plus 5 plus a constant. This is partial fractions. Any questions? Yeah.
Would you do the same thing if it was the trinomial?
If it was a trinomial on the bottom, yes, that is the next chapter in this story is what if we had a, third order polynomial in the denominator, right? How's that go? Well, what is possible for a third order polynomial in the bottom, in the denominator? What are different kinds of third order polynomials that you'd confront? Do you know? Let's talk about possible patterns for a third order in the denominator. So here's the deal. Suppose we have a quadratic. Well, first of all, if we have a cubic over a cubic, right? Or really, let's just say, what did I say, p of x up here? And if p of x has degree of p of x greater than or equal to 3, you'll need to do long division to begin. Right? We'll come back to that. Otherwise, we're looking at something like a quadratic polynomial over a cubic, right? Something like a quadratic over a cubic, generically speaking. Let me be more generic. In other words, there exist, well, actually, I think that's enough. I mean, does it help you to me write something like a1x squared plus b1x plus c1 divided by like a2x cubed plus b2x squared plus c2x plus d2, something like that? I mean, generically speaking, something like that. So the structure of the partial fractions decomposition depends on the nature of the cubic. If we have a cubic, what are the different ways it can factor? It could be distinct linear, right? You could have linear repeated, and then another distinct linear from that. You could also have a irreducible quadratic times a linear factor. So let's see, is there anything else? Oh, you could also have a linear factor three-peated. You're like, that's not a word. Well, you know what I meant. Or do you know what I mean? Maybe not. Let me give examples of each case. Let me give examples of each case. So, case one, distinct linear, something like, and let me just say that, you continue using the notation P of x over Q of x, if you don't mind. I was trying to find a different color. I've got like 4 blue markers over there. Contrast of blue on blue, not so awesome. Sorry if you're colorblind. Let's see here. Q of x could be something like x minus 1, x minus 2, x minus 3, But generically speaking, x minus r1 times x minus r2 times x minus r3, where r1, r2, and r3 are not equal. This would be just a pair of distinct, distinct repeated, something like this. Q of x could be something like x minus, instead of giving an example, let me just, fine, I'll give an example. X minus 1 squared, I have trouble with decision making. Let's see here. So x minus 1 squared times x minus 2, that's another kind of cubic factorization we could face. Irreducible quadratic would be something like Q of x equals to, well, we were just looking at this a second ago, x squared plus 4x plus 5 times, I don't know, x plus 1, whatever. It could be even x plus 2, that would still be distinct. Like the fact that there's an x plus 2 in the completing the square of the x squared plus 4x plus 5, that doesn't count, right? So that's another kind of cubic factorization. And then finally, there's also this one, right? Just a perfect triple. Those are your choices. These are the possible ways a cubic can factor, right? Is there anything else? Yeah. They always factor. There's always a linear. Okay, so here's the logic for that. If we're talking about a real cubic, right? You can prove that it's going to take on a positive and a negative value. All right? And then, since it's continuous, the intermediate value theorem says it has to take a value of 0 between where it takes positive and negative value. But then, if it has a value of 0, the factor theorem of algebra says that we can factor out a linear factor. Then what's left is a quadratic factor. And we can figure out where the quadratic factor is 0 by the quadratic formula or other means. And that leads to these 4 cases. There's always at least one linear factor in all of these, right? And then what's left over is either a distinct quadratic, a distinct quadratic which partially overlaps with the linear, or a repeated quadratic which completely overlaps with the linear factor, or an irreducible quadratic which doesn't overlap with that initial linear factor. Anyway, these are the cases. And so, in each one of these cases, there is a distinct kind of partial fractions decomposition you look for. All right? I'll tell you what they are. Yeah, there's an example missing from my quadratic case. What was the example that's missing? Yeah, we'll come back to it. So this one would suggest a partial fractions decomposition of something like a over x minus 1 plus b over x minus 2 plus c over x minus 3 for this case. For the second case, you use a partial fractions decomposition like a over x minus 1 plus b over x minus 1 squared plus c over x minus 2. That's the partial fractions decomposition in that case. For this one, I would do something like a times x plus 2 plus b over x plus 2 squared plus 1. That's the irreducible quadratic there. Plus c over x plus 2. For this one, the partial fractions decomposition is a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. So I've accidentally left something out of the quadratic discussion. I need to go back and fix it before we continue with the cubic, because by now there's two things here. If you're a thinker, they're bothering you. Like this, right? And this, like what am I doing there, right? So something I could do that might be convincing to you, I don't know, we'll see. Possibly helpful exercise in algebra. So let's try something out. Let's try to look at 1 over x plus 2 plus 3 over x plus 2 squared. What's that equal to? If I want to make that into a single rational function, what do? You make a common denominator, right? So you just say, okay, so that's x plus 2 over x plus 2 times x plus 2. Right? Just multiply the first fraction by x plus 2 over x plus 2. And then that gives us x plus 5 over x plus 2 squared. So this is the thing we're seeing. The observation is this. If we have something like ax plus b over x minus c squared, then we probably can rewrite it as ax plus b over x minus c squared equal to some constant, let's say big A, over x minus c, plus some other constant big B over x minus c quantity squared. The right-hand side of what I just wrote is the partial fractions decomposition in this case of a repeated linear factor. Why do we prefer the right-hand side to the left-hand side of what I just wrote? What's that? Yeah, exactly. This, we can integrate. Easy. This, maybe, maybe not. I don't know. Okay? So the reason I'm mentioning this is because in the discussion of the different possibilities for a cubic, we saw that same kind of thing appearing here in this case, right? But also, if it's three-peated, then you do the same thing, but with the x minus 1, the x minus 1 squared, the x minus 1 cubed, like that. There's a very big difference between if the quadratic you're looking at has a repeated root versus if it's irreducible. We treat the irreducible factors different than we treat the linear factors, all right? So let us look at one. What example am I on? 4. Example 4. Okay, thanks. Let's find partial fractal decomposition for f of x equal to, let's say, x squared plus 1 over x cubed plus, well, x cubed minus 3x squared plus 3x minus 1. Or plus 1, rather. I'll make it all pluses. I'm sorry. I'll get with the program eventually here, guys. So what are we looking at? What's that? All right, that is x plus 1 cubed. Nah, you thought that was never coming back, huh? It's back. Okay, just for this example, though. So the partial fractions decomposition has the following form. It's a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. So how do we find a, b, and c? Yeah, multiply by the denominator. Well, what does that give us? Enough of this marker. Man, my bank shot is off. All right. That gives us x squared plus 1 equals to a times x plus 1 squared plus b times x plus 1 plus c. I will call this Pac-Man. So let me introduce a new notation. Well, I mean, I've already introduced it, but let me use it now. Yum, 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 yum. See, imagine the Pac-Man eating the minus 1. And then, so that's 0. That's 0. We're just left with c. Now, we'd like to feed Pac-Man other distinct roots here, but we've only got -1, right? So the trick we've been doing on the past couple of examples not going to work for us here, is it? There are various ways to proceed. The key here, though, is that Pac-Man equation holds for all x, right? We're trying to find a, b, and c such that this holds for all the values of x. So one thing you can do is to differentiate Pac-Man. So dPac-Man dx equal to 2x equals to 2a times x plus 1 plus b, right? And if we feed Pac-Man prime -1, actually that's not the right word, I should say nom 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 nom. Nom nom nom. Feed Pac-Man prime the -1, what's it give you? Nom 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 nom. -2 equal to what? Oh, you said b? Yeah. So apparently, b is equal to -2, right? And then, of course, if Pac-Man holds for all x, dPac-Man dx holds for all x, so what do you think we're going to do? What's the laziest way to solve this algebra problem? What's d squared Pac-Man dx? That's 0 equals to 2a. Hey, we don't even need to feed this anything. It already tells us that a is equal to 0, right? Yep. The derivative of 2a times x plus 1 is just 2a. Oh, it was 2x?
Yeah.
Oh, thank you. I've made the unfortunate but popular mistake of confusing the evaluation of the derivative with the derivative, which is a bad mistake. Sorry about that. But you're right, that 0 should be a 2, which is much more exciting because now we found out that a is equal to 1. Thank you. So, long story short, what did we just figure out? We just figured out that the integral, I mean, I'm coming back to integration now because, you know, that is ultimately our aim. But you see, we could ask questions just about the algebra here, independent of the integration question, yeah? And sometimes I do that on the test. I'll just say find the partial fractions or set up the partial fractions and not even worry about the integration that follows. But, you know, I think the integration that follows is interesting, so I'm talking about it. Okay, x plus 1 minus 2 over x plus 1 squared, yeah? What was my c? Oh, yeah, plus 2 over x plus 1 cubed. So this is going to be the integral of 1 over w minus 2 over w squared plus 2 over w cubed dw setting what? W equal to x plus 1, right? Because dw is equal to dx. Just, I mean, I haven't put this step down before because it's always been a little bit, I mean, this step I just wrote down, I'm not sure it absolutely needs to be written in this class, but there it is. And so what I got is I got natural log the absolute value of w minus what? Well, plus 2 over w, right? Because the integral of 1 over w squared is minus 1 over w. So the 2 rides along and the minuses cancel. If you don't believe me, differentiate 2 over w. What does it give you? It gives you minus 2 over w squared, which was what we were anti-differentiating. And how about the next one? Well, that's, I believe that's just minus 1 over w squared. If we differentiate w to the minus 2, what do we get? right, minus 2 over w cubed. But we got the 2 there already, and so I just have to put a minus in to be safe. And okay, going back to what w is, that's the natural log Laplace value of x plus 1 plus 2 over x plus 1 minus 1 over x plus 1 squared plus a constant. Any questions? Let's see here. I made up an example for us to do. This one, I see that's still not. Sorry, I don't have a. I'm not sure if I have a good long division example right off the top of my head. I see if I can find one. I don't like to just make them up. If I make them up, it could go very badly. Well, you worthless. Well, that's kind of okay. I guess I'll have to be content with this example. What was the question? A question? So if we had 2x cubed plus x squared minus 7x plus 7 over x squared plus x minus 2, if we had to integrate that, the first thing we would need to do is to rewrite it as the sum of a polynomial. We want to rewrite this as the sum of a polynomial plus, p of x over x squared plus x minus 2, where this is linear. Right? That's our goal. That's what long division does for us. All right. So let me show you how that goes. So what we do is we write 2x cubed plus x squared minus 7x plus 7. And we're going to divide x squared plus x minus 2 into that. So you go, okay, well, I gotta kill off that 2x cubed term, right? So in order to do that, I have to multiply x squared by 2x. So that gives me 2x cubed plus 2x squared minus 4x. So what I've done is I've taken the 2x and I've multiplied that by the dividing polynomial, the x squared plus x minus 2. That gave me 2x cubed plus 2x squared minus 4x. I then subtract that from the given numerator, right? And the 2x cubes cancel, and that gives us minus x squared minus 3x plus 7. All right? Then the question is, how can I get rid of that minus x squared with the given dividing polynomial? Well, with a given divisor, minus 1. I just do minus 1, 2x minus 1 up here. And then that gives me minus x squared minus x plus 2. Bless you. And then again, we have to subtract. And when we do that, the x squareds minus x squareds cancel, and we're left with minus 2x plus 5. All right. So this algorithm continues until the point that when you take the difference, you get something that is of smaller degree than the divisor, right? But here the remainder, right, minus 2x plus 5 is degree 1, whereas we're dividing by a quadratic. We're done. That's the remainder. So this is the so-called remainder. And so what this shows us then is that 2x cubed plus x squared minus 7x plus 7 over x squared plus x minus 2, well, that's equal to 2x minus 1 plus, let's say, 5 minus 2x divided by x squared plus x minus 2. So there's my polynomial and then my proper rational function. And then we could integrate that. Right? Well, actually, not yet. What would we have to do on the proper rational thing? Factor it. Does that factor? I think that's x plus 2 times x minus 1. So that would be like example 1. All right? I lost my... Where did I put my example? All right. Some just quick setup example, quick setup. So just state partial fractions decomposition. Don't find A, B, C, etc. All right. So let's see here. What example am I on? 5. Here we go. If you had something like x cubed plus 7 divided by x squared minus 1 times x squared plus 1, you factor. That's x minus 1 times x plus 1 times x squared plus 1. Right. Now, we haven't worked an example like this all the way through yet, but here's how the partial fractions goes through something like this. You just kind of take a combination of what you've already done. So it's something like a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1. That's how that would go. If you had something like x cubed plus 7 over x squared minus 1 squared times x squared plus 3x plus 2. So the first order of business is to factor the denominator. Right? Once you have factored the denominator cleanly, then you can read off the partial fractal decomposition. So how does the denominator here factor? We've got what? X minus 1 times x plus 1 squared. Both of those are squared. And then x plus 1 times x plus 2